Something left the sun at 1:36 in the morning on June 3rd, 2026, and it was heading straight for us. Not a beam of light, not a radio wave. Something physical, something with weight, with momentum, with its own magnetic personality. A cloud of charged particles the size of a continent, actually bigger than a continent, bigger than several continents stacked on top of each other, ripped loose from the surface of the sun and flung outward into space at speeds that make anything humans have ever built look like it is standing still. And the direction it was heading, according to the instruments at NOAA's Space Weather Prediction Center in Boulder, Colorado, was Earth. This is the story of the week that the sun reminded us. It is still in charge. We spend a lot of time worrying about things that are close to us. The economy, the weather, traffic, the news cycle, things we can see and touch and vote on and argue about. We do not spend a lot of time looking up. But the sun, that thing 93 million miles away that you probably have not thought about today except maybe to squint at it through a car window, is not a stable, quiet, gentle ball of light. It is a churning, violent, magnetic monster that is currently in one of the most active phases it has entered in decades. And this week it threw something at us. Twice. In 6 days. From 2 different locations on its surface. And the second one is arriving right now. Today, June 8th, 2026. As you read this, so let us slow down. Let us really dig into what happened, why it matters, and what it means for you personally. For your power, your phone, your GPS, your flight, your daily life. Because this is not abstract science. This is something that reached into the infrastructure of modern civilization this week and shook it, and most people have no idea it happened. Let us start from the very beginning. Because to understand why the events of early June 2026 matter, you need to understand what is actually happening on that ball of fire 93 million miles from your front door. And once you understand it, you will never look at a sunny day quite the same way again. The sun is, at its most basic level, a ball of plasma. Plasma is just matter in a state you do not normally encounter in everyday life. It is what happens when you heat a gas so intensely that the electrons get knocked off the atoms entirely. So instead of neutral atoms moving around, you have a soup of positively charged nuclei and free electrons, all moving independently, all interacting with each other through electromagnetic forces. This matters enormously, because charged particles in motion create magnetic fields. This is the same principle that makes your electric motor spin, that makes your speakers work, that makes every generator in every power plant on Earth operate. Moving charges equal magnetic fields. It is not negotiable. It is how the universe works. In the sun, this plasma is constantly in motion. Enormous convective currents carry hot material up from the deep interior, let it radiate energy at the surface, and then pull it back down again as it cools. A process not entirely unlike the way a lava lamp works, except the lava in this case is millions of degrees hot and the lamp is 1,000,000 miles across. These convective flows drag the magnetic field lines along with them, stretching them, twisting them, wrapping them around each other. Over days and weeks and months, this process creates regions where the magnetic field becomes extraordinarily intense and extraordinarily tangled, like a ball of rubber bands that has been stretched and twisted and knotted until it is holding an almost unimaginable amount of stored energy. Those regions of intense magnetic activity are what we see as sunspots when we look at the solar surface through a filtered telescope. Sunspots appear dark because the intense magnetic field in those areas suppresses the normal convective flow that brings heat up from below. The surface in a sunspot is cooler than the surrounding photosphere. Cooler in relative terms, that is, because even a sunspot is thousands of degrees. But relative to the blinding brilliance of the surrounding surface, a sunspot appears dark, like a bruise on the face of the sun. And here is the critical thing about sunspots. They are not peaceful places. They are the locations of maximum magnetic stress on the solar surface. The magnetic field lines threading through and around a sunspot group are under enormous tension, like stretched rubber bands pulled to the point where they are about to snap. And when they do snap, when the magnetic field lines break and reconnect in a new configuration through a process called magnetic reconnection, the energy released is staggering. We are talking about the equivalent of billions of nuclear weapons going off simultaneously. That release is a solar flare, and a solar flare is how this entire story begins. When a solar flare fires, 2 things happen more or less at the same time. First, a burst of X-ray radiation and extreme ultraviolet light races outward from the sun at the speed of light. This radiation reaches Earth in about 8 minutes, the same 8 minutes it takes visible sunlight to make the journey. When it arrives, it hits the upper atmosphere on the daylit side of Earth and ionizes it, stripping electrons off atoms in the thin upper layers of air. This ionization dramatically changes the electrical properties of that atmospheric layer. and one of the most immediate consequences is that shortwave radio, the high-frequency radio signals between roughly 2 and 30 megahertz that bounce off the upper atmosphere to communicate across vast distances, gets absorbed instead of reflected. The sky goes radio dark on the sunlit hemisphere, ships lose contact with shore, pilots lose their oceanic radio links, emergency services in remote areas lose their backup communication systems. This is called a radio blackout, and it happens at the speed of light, 8 minutes after the flare fires, with zero additional warning. The second thing a solar flare does is potentially more consequential, but takes much longer to arrive. Under the right conditions, depending on the geometry of the explosion and the specific magnetic configuration of the source region, the energy of the flare can literally blow a piece of the sun's outer atmosphere off into space. An enormous bubble of magnetized plasma containing billions of tons of material gets flung outward at speeds that can range from a few hundred to a few thousand kilometers per second. This is the coronal mass ejection, the CME, and it is the thing that 2 to 3 days later hits Earth's magnetic field and produces the geomagnetic storm. The flare is the muzzle flash. The CME is the bullet with that foundation in place. Let us talk about the specific piece of the sun that started all of this trouble in early June 2026. Because active region 4455 was not an ordinary sunspot group, it was unusual in ways that made it more dangerous, more productive, and genuinely harder to predict than a typical region. AR 4455 first showed up in the awareness of the global space weather community in late May 2026. Even while it was still rotating around the far side of the sun, the side facing away from Earth, instruments were picking up signs of activity from it. When it finally came around the northeastern limb of the solar disk and into direct view, it was already leading all other sunspot groups in flare production. Observers who photograph the sun through filtered telescopes and share their images with the solar monitoring community were posting detailed pictures of this region as soon as they could get it in frame. On May 29th, before it was even fully visible, it fired an M1 flare that triggered a minor radio blackout over India. It was announcing itself early, and what people saw in its structure was impressive. A large, complex sunspot group with multiple dark cores, intricate magnetic field architecture visible in specialized wavelengths, and a configuration that put it in the top tier of flare-productive regions before it had even fully rotated into view. But AR 4455 had a specific characteristic that made solar physicists pay especially close attention. It had what researchers call an anti-Hale magnetic configuration. This is one of those phrases that sounds like pure scientific jargon, but actually describes something quite intuitive once you have the context. The sun's magnetic field operates on an 11-year cycle. During any given cycle, the sunspot pairs that form in the northern hemisphere of the sun follow a consistent rule about which end of the pair is positively magnetized and which end is negatively magnetized. Think of each sunspot pair as a bar magnet lying on the sun's surface. One end is the North Pole, one end is the South Pole, and during any given solar cycle, every pair in the northern hemisphere has the same orientation. This pattern was discovered by the American astronomer George Ellery Hale in the early 1900s, and it is called Hale's polarity law. It is one of the most reliable regularities in all of solar physics. It holds true for approximately 97% of all sunspot groups that form on the sun. R455 was in the other 3%. Its magnetic polarity was inverted, flipped. The positive and negative poles were on the wrong ends relative to what solar cycle 25 predicts. This inversion happens because the magnetic flux tubes rising from deep inside the sun have been twisted or distorted, probably by turbulent convective flows in the solar interior, in a way that reverses their polarity before they break through the surface. The exact mechanism is still an area of active research in heliophysics. What the consequences are, however, is much better understood. An anti-Hale configuration creates a specific kind of internal magnetic stress that standard sunspot groups do not experience in the same way. The field lines inside an anti-Hale region are forced into configurations they are fighting against, orientations that the surrounding global field is actively trying to correct. The energy builds up differently, it can release differently, and the forecasting algorithms that operational space weather centers rely on every day to estimate flare probability, algorithms that have been trained and calibrated on the 97% of regions that follow Hale's law, can significantly underestimate the risk from the 3% that do not. Research cataloguing anti-Hale regions going back to 1989 has confirmed what operational forecasters have long suspected. These regions are disproportionately associated with high flare productivity and with the initiation of strong geomagnetic events. They are the outliers that the models were not built for. This is exactly what happened on the morning of June 3rd. AR4455 had been assessed as carrying a relatively modest flare risk for its size. The magnetic configuration in the standard classification scheme looked simpler than it actually was, because the anti-hail structure confuses the automated complexity scoring algorithms. And then, in a 10-hour burst that nobody's prediction tools had fully anticipated, the region produced 3 of the most significant flares of the year. It started at 122 Unit-Alcine. The X-ray detectors aboard the GOES-19 satellite, one of NOAA's twin geostationary weather satellites orbiting 22,000 miles above the equator, picked up the beginning of a significant brightening from the direction of AR4455. The signal climbed. It crossed the M1 level, which is the entry point for what scientists classify as major flares. It kept climbing M3, M5, M7. It peaked at M9-3 at 136 Q/T, and the entire event from start to finish lasted from 122 to 143, 21 minutes of sustained, high-energy output from one of the most stressed patches of magnetic field on the surface of the Sun. Let us pause here and talk about the flare classification system, because it is actually one of the simpler scientific scales to understand once someone explains it without jargon. Solar flares are rated in 3 main categories: C, M, and X. C-class flares are the most common significant ones. They happen frequently during solar maximum and typically cause minor, brief radio disturbances. M-class flares are the middle tier, major flares capable of causing significant radio blackouts and launching Earth-directed CMEs with real storm potential. X-class flares are the top of the scale, the most powerful category, the ones that make news, the ones that drive the strongest storms and the most significant infrastructure consequences. Within each letter category, a number from roughly 1 to 10 specifies the intensity within that tier. M9.3 is right at the edge of the X-class boundary, so close that some space weather communicators informally call events in the M8 and M9 range near X flares. AR4455 was starting its day of infamy with a shot right at the upper limit of the M range. The radio blackout from the M9.3 rated R2, or moderate on NOAA's radio blackout scale, hit the Pacific Ocean region. Ships in the Central Pacific, aircraft on transoceanic routes, Coast Guard stations across the Pacific Basin, maritime rescue coordination centers from Hawaii to Japan, all experienced degraded or lost shortwave radio communications for the duration of the blackout. For most of them it lasted minutes. For some, in the frequencies most affected, it was longer. Within minutes of the flare's peak, analysts at NOAA's Space Weather Prediction Center were reviewing coronagraph imagery from the SOHO spacecraft. The Solar and Heliospheric Observatory, a joint NASA-ESA mission that has been watching the Sun continuously from its vantage point 1.5 million miles sunward of Earth since 1995. SOHO carries an instrument called the LASCO coronagraph, which works by blocking out the main disk of the Sun with an artificial obstruction, essentially creating a permanent artificial solar eclipse, and photographing only the Sun's outer atmosphere, the corona. This allows scientists to see CMEs emerging from the Sun, which would otherwise be completely invisible against the overwhelming brightness of the solar disk itself. By 213 imagery, LASCO C2 imagery showed a structure emerging from the direction of AR4455, faint but real. The geometry of AR4455's position in the Earth-facing zone made the Earth-directed component clear. A CME was confirmed. SWPC notified the relevant operational partners and began tracking. Then AR445 fired again, 5 hours and 24 minutes after the M9. At 7:03 in the morning for people on the east coast of the United States and midnight on the west coast, the region erupted with an M77 flare. The event started at 6:48 UTC and ended at 7:07. NOAA's GOES-19 solar ultraviolet imager captured it in detail, showing the bright flash in the northwest quadrant of the solar disk. This flare produced an R2 radio blackout affecting communications over India and the surrounding region, which at 7 UTC was in the middle of a business morning, with air traffic controllers, maritime operators, military communication units, and shortwave radio users of every kind depending on those frequencies for operational communication. NASA's Solar Dynamics Observatory, the spacecraft that provides the most detailed continuous imagery of the Sun in multiple wavelengths, confirmed another major CME launched into space from the direction of AR4455, another Earth-directed component identified, another cloud of magnetized plasma now beginning its 2 to 3 day journey across the solar system. The SWPC team was now tracking 2 separate clouds of solar material simultaneously, running both through the WSA-Enlil solar wind propagation model, the computational simulation that models how CME clouds travel through the varying conditions of the interplanetary medium to estimate arrival times, speeds, and potential storm intensity at Earth. And then, without much additional warning, AR445 crossed the line into X-class territory. at 11:28 in the morning Eastern, 4:28 a.m. Pacific. The region erupted for the third time. The GOES X-ray flux monitor spiked past the M10 threshold and into X territory. It peaked at X17 at 11:48 time, an X-class solar flare, the most intense category on NOAA's scale. The threshold that makes operational space weather forecasters sit up very straight and start making phone calls to grid operators, satellite managers, and aviation authorities. The X107 triggered an R3 radio blackout, rated strong on NOAA's scale, affecting the sunlit face of Earth at that moment. At 11:28 QUT, the daylit hemisphere included a band running from Central Asia across the Pacific toward the Americas. HF radio communications were degraded or completely interrupted across parts of Asia, Europe, Africa, Australia, and the Pacific simultaneously. Every pilot on a long-haul oceanic route in that zone, every ship's radio operator calling in a position report, every emergency services unit depending on shortwave backup, all of them hit a wall of radio silence that lasted from several minutes to most of an hour in the most affected frequency bands. The X1.07 also produced a 7 centimeter radio burst peaking at 250 solar flux units, a measure of the intensity of solar radio emission that the space weather community uses as a proxy for overall solar activity level. And in the coronagraph imagery that followed, with the additional CME structure becoming visible shortly after, forecasters now had a 3 CME scenario to track. 3 separate clouds of magnetized plasma, launched by 3 separate explosions from the same sunspot group within 10.5 hours, all heading in the general direction of Earth. The final count for June 3rd. 11 of the 14 solar flares that fired on the entire sun that day came from AR4455. This single sunspot group produced every M-class and X-class event of the day, M93, M7.7, M13, M3M7, plus 6 additional C-class flares. It was the most flare-dominant single day from a single active region in months, and it did so while being classified, based on standard magnetic complexity metrics, as lower risk than its actual behavior demanded. The anti-hail configuration had done exactly what the research literature predicts it does. It fooled the forecasting tools and delivered a surprise. Here is where the story goes from interesting to genuinely remarkable. Here is where the term Cannibal CME enters the picture, and despite the dramatic name, the physics behind it is something you can understand very easily using an image that everyone who has ever driven on an American highway will recognize immediately. Picture a highway, a long, straight, flat American interstate on a summer afternoon. 3 cars leave the same on-ramp at different times, all going the same direction, all heading toward the same destination city hundreds of miles down the road. Car 1 leaves at 1:36 p.m., cruising at 55 miles per hour. Car 2 leaves at 7 p.m., moving faster at 70 miles per hour. Car 3 leaves last at 11:48 p.m., driving at 90 miles per hour. All 3 are heading to the same place. What happens? Car 3, the fastest, starts gaining on Car 2 almost immediately. Car 2 is gaining on Car 1, and by the time they have been on the road for several hours, or in the real cosmic scenario, for several tens of millions of miles, the faster cars catch up. And in the CME version of this story, when a faster cloud of solar plasma catches a slower one in the open interplanetary space between the Sun and Earth, they do not politely signal and change lanes, they merge. The faster cloud plows into the trailing edge of the slower cloud, compresses it, sweeps it up, and the 2 structures combine into one larger, denser, more energized structure that continues toward Earth, carrying the combined momentum and magnetic energy of both original clouds. This is a Cannibal CME. The term is vivid but accurate. The faster ejection literally consumes the slower one, incorporates it into a combined structure that is more dangerous than either component individually would have been. The leading edge of the merged cloud, the shock front, is more compressed, more energized, and carries a higher magnetic field strength than either original CME would have generated alone. When that combined structure hits Earth's magnetosphere, it hits harder. It carries more energy into the geomagnetic environment. It drives a stronger storm. There is an additional complication that makes Cannibal CMEs particularly tricky to forecast. When 2 CME clouds merge in transit, the interaction between their magnetic fields creates a more complex internal magnetic structure in the combined mass. The organized field structure that each CME started with, which solar physicists use to make educated guesses about the busy orientation, the critical magnetic field direction that determines storm severity, gets scrambled by the merging process. The combined cloud arrives at Earth with an internal magnetic field that is harder to predict from the source event characteristics alone. You have less information going in about whether the combined structure will drive a violent storm or a moderate one. The uncertainty envelope gets wider, According to analysis of NOAA's GOES-19 SUVI instrument imagery reviewed by EarthSky's solar team in their June 4th briefing, some of the M7 CME material was deflected northward by a stream of fast solar wind coming from a coronal hole located just south of AR 4455. A coronal hole is a region of the Sun where the magnetic field lines open up and point outward into space rather than looping back to the solar surface, allowing solar wind to escape at higher than normal speeds. Think of it as an opening in the Sun's magnetic atmosphere, where the wind can pour out freely rather than being contained and recirculated. The fast stream from this particular coronal hole pushed against the southern flank of the M7.7 CME and bent a portion of it northward above Earth's orbital plane, but only a portion, the remaining Earth-directed fraction of the M7. 7 material combined with the faster material from the X-17 flare overtaking it from behind, forming the merged Cannibal CME that SWPC was tracking by the morning of June 4th. The formal watch was issued at 9:17 p.m. UT on June 3rd. G3, strong geomagnetic storm watch in effect for June 4th and June 5th. This was not a warning that the storm was already happening. A watch, identical in concept to a tornado watch, means the conditions exist for the forecast event to occur. The ingredients are present. The threat is real. You should be paying attention and ready to act if conditions develop. The storm itself would begin when the merged CME cloud arrived at Earth and started interacting with the magnetosphere. To understand what the G3 watch meant in practical terms, you need to understand the scale. NOAA rates geomagnetic storms on a 5-level system that runs from G1 at the bottom to G5 at the top. The letters and numbers correspond to specific measured thresholds in the planetary K-index, the globally averaged measure of geomagnetic disturbance that space weather scientists use to quantify how agitated Earth's magnetic field is during a solar event. G1 is minor. The KP index reaches 5. These storms happen fairly often during solar maximum, perhaps 50 or more times in a solar cycle. The main consequence most people might notice from a G1 is that the aurora could be visible slightly further south than usual on a clear, dark night. Your power stays on, your GPS works fine, your phone has full bars. Life continues completely normally. G1 is a space weather event that the infrastructure of modern civilization handles without breaking a sweat, because the systems were designed with normal solar variability in mind, and G1 is firmly within that range. G2 is moderate. KP reaches 6. These happen perhaps 30 times in a solar cycle. At G2, high-latitude power systems start seeing voltage irregularities that require automated correction. Transformers at some high-latitude substations experience mild elevated thermal stress from geomagnetically induced currents. Satellites in low Earth orbit experience slightly increased atmospheric drag and may need more frequent thruster burns to maintain their orbital positions. Some high-frequency radio communication is affected, particularly on polar routes. Aurora can be seen in northern tier states on clear nights. The grid handles it, the satellites handle it, the airlines adjust their communication protocols, and most people still never notice anything unusual. G3 is strong, KP reaches 7. This is the level of the June 4th watch and the June 8th watch we are dealing with right now. G3 storms happen roughly 10 to 15 times in a solar cycle. Power utilities at high latitudes, not just Canada and Scandinavia but northern Minnesota but Montana, Wisconsin, Michigan, New England and the Pacific Northwest, start seeing voltage corrections that their automated systems have to work harder to manage. Some protective systems on power lines may require manual intervention. Spacecraft operators receive formal notifications and begin protective protocols for their satellites. GPS accuracy degrades measurably and persistently. HF radio on high latitude and polar routes becomes unreliable for extended periods, and the aurora pushes down to roughly the 50-degree geomagnetic latitude line, which in the United States includes Oregon, Idaho, Wyoming, South Dakota, Wisconsin, Michigan, New York, and all of New England. G3 is visible, G3 is felt. G3 causes real operational challenges when it arrives without adequate preparation. G4 is severe, KP reaches 8. These are rare, perhaps 3 or 4 per solar cycle. Widespread voltage control problems in power systems. Some protective systems trip, causing localized outages that last hours rather than minutes. Satellite navigation errors become significant enough to affect aviation procedures and precision navigation. HF radio communication is largely impossible on polar routes. Aurora visible as far south as Alabama and Northern California under the right conditions. At G4, grid operators seriously consider controlled load shedding, deliberately cutting power to some areas to protect the larger system from more severe damage. G4 is the level where the event makes national news and emergency managers take active roles. G5 is extreme. KP reaches 9. This is the level of the Carrington event, the Halloween storms of 2003, and the May 2024 event that put the northern lights over Mexico. Complete HF radio blackout for many hours, GPS unreliable for days, aurora seen in Hawaii, Cuba and the tropics, extensive surface charging on satellites that can damage electronics, pipeline companies detecting large induced voltages that can accelerate corrosion, and for the power grid, the foundation that everything else sits on, the real possibility of widespread, prolonged outages driven by transformer failures that take months to fix. G5 is where the conversations stop being about operational protocols and start being about emergency management, national resilience, and the kind of systemic risk that keeps infrastructure security professionals awake at night. We are dealing with G3 this week, serious, real, consequential, and 2 full steps below the most extreme level the Sun is capable of producing. Keep that calibration in mind as we continue. The story is significant without needing to be inflated. The Cannibal CME from the June 3rd flares arrived at Earth around 4:30 on June 5th. The DSCOV spacecraft, positioned at the L1 Lagrange point 1.5 million miles sunward of Earth, at the gravitational balance point between our planet and the Sun, detected the sharp jump in solar wind speed that marks the arrival of a CME shock front. DSO is the Sentinel, the early warning system, the spacecraft whose entire purpose is to sit in the interplanetary medium and measure what is coming before it reaches Earth, giving ground-based operators between 15 minutes and an hour of additional preparation time. When DSCOVR's instruments registered the arrival, automated alerts went out across the Space Weather Notification Network grid operators in Canada. The northern United States and Scandinavia received their storm notifications. Satellite operators received NOAA bulletins and began checking spacecraft status, adjusting orientations where needed. FA advisory notices went to aviation weather services. Airlines reviewed their contingency plans for high-latitude route rerouting. By 5:36 p.m. UTC on June 5th, NOAA officially confirmed that G2 moderate conditions had been reached. G2 geomagnetic storm levels reached following the likely arrival of the anticipated CMEs from June 3rd. That was the language of the official SWPC bulletin. The Cannibal CME had arrived, it was interacting with Earth's magnetic field, and it had come in at G2 rather than the forecast peak of G3. Why did the storm underperform the peak forecast? The most likely explanation is the coronal hole fast wind stream that deflected a portion of the M7 material northward before the merger could fully complete. Less total mass in the Earth-directed portion of the combined structure, and potentially a less favourable BZ orientation in what did arrive, kept the storm at G2. This kind of forecast versus reality gap is normal and expected in space weather prediction. The models are good, but the physics of CME propagation through the varying interplanetary medium introduces uncertainty that cannot be fully eliminated with current observational assets. But G2 had real consequences. Power utilities across the northern tier of North America logged voltage fluctuations that their automated management systems corrected in real time. Large high-voltage transformers at major substations through Ontario, Quebec, Manitoba, the Pacific Northwest and the Upper Midwest experienced elevated thermal stress from geomagnetically induced currents flowing through the ground and into the transmission system. The ground currents that drive this effect are a direct physical consequence of the rapidly changing magnetic field during the storm. The changing field induces voltages in any long conductive object in the ground, and power lines are among the longest and most conductive objects humans have ever built in Scandinavia, where the combination of high magnetic latitude and the highly resistive bedrock geology of the ancient Precambrian shield makes GIC effects particularly intense. Utility operators reported elevated transformer temperatures at several high-voltage substations. Margins got smaller, maintenance crews took note, nothing failed, but the equipment was working harder than it does on quiet solar days. GPS accuracy degraded across North America and Europe during the storm. Ionospheric irregularities driven by the geomagnetic disturbance bent and scattered the satellite navigation signals in ways that exceeded the error correction capacity of standard receivers. Positioning errors of 10 to 20 meters became common in affected regions. For most users, people checking a map on their phone, navigating to an unfamiliar restaurant, tracking a package delivery, this was completely invisible. For precision applications, survey crews, precision agriculture systems, construction layout work, search and rescue operations, it was operationally significant. Satellites in low Earth orbit experienced measurable increases in atmospheric drag as the upper atmosphere expanded in response to the storm's energy input. The International Space Station, the Starlink constellation, OneWeb satellites, weather satellites, Earth observation spacecraft, all of them logged slightly elevated drag signatures in their orbital tracking data. Satellite operators increased the frequency of their thruster burns to maintain orbital positions. Fuel was consumed, operational life was marginally reduced, and HF aviation radio degraded on high-latitude routes throughout the storm period. Airlines operating transpolar routes between North America and Asia and on North Atlantic tracks between North America and Europe experienced the communication challenges that the X1x7 radio blackout on June 3rd had previewed. Crews switched to satellite communication backups. Some flights accepted slightly longer routing to maintain better HF coverage. The North Atlantic Organized Track System shifted traffic toward lower latitude tracks. These are standard operational adjustments with well-established procedures, but they represent real costs in fuel, in time, in crew workload, that get absorbed every time a significant solar event occurs. Then, before the June 3rd storm had even fully cleared, the sun fired again at 2:01 p.m. UTC on June 6th. Just as the CME patch from June 3rd was winding down and conditions were beginning to return toward normal, active region 461 produced an M18 solar flare. AR4461 was a newcomer, a different and smaller sunspot group that had received its official NOAA designation only days earlier and was located in the southeastern quadrant of the solar disk. The M18 flare itself was not remarkable by the standards of solar maximum. M1, 8 flares happen regularly. What made this event significant was what accompanied it: a filament eruption. A solar filament is one of the more visually striking and scientifically important structures in the solar atmosphere. Filaments are long, dark, rope-like threads of relatively cool, dense plasma, much cooler than the surrounding corona, suspended above the solar surface by magnetic field lines. If you have ever seen images of the sun taken in hydrogen alpha light, the specific deep red wavelength that shows the chromosphere in striking detail, you have seen filaments. They look like dark rivers or channels running across the face of the sun, sometimes stretching for hundreds of thousands of kilometers in length. They exist in a precise, delicate balance between the downward pull of solar gravity and the upward magnetic tension of the field lines holding them in place above the surface. When that balance breaks, when the magnetic field structure supporting the filament becomes unstable due to the emergence of new magnetic flux from below, or the slow evolution of the surrounding field configuration, or the trigger of a nearby flare, the filament erupts. The magnetic tension that was holding it up fails, and the heavy rope of cool plasma collapses and is flung outward into space. A filament eruption combined with a solar flare can produce a CME that is both more massive and more magnetically complex than a flare-only event, because the filament material itself carries a distinct magnetic signature that merges with and modifies the CME produced by the flare. The partial halo CME that the AR4461 event produced became visible in LASCO C2 coronagraph imagery at approximately 2:01 p.m. UTC on June 6th. SWPC forecasters began their analysis immediately. The WSA and model runs were initiated, and by 10:15 p.m. UTC on June 6, less than 9 hours after the event, NOAA issued a new formal watch, G3 Strong Geomagnetic Storm Watch for June 8, 2026, G2 Moderate Watch for June 9th. The CME from the June 6 AR4461 event was forecast to arrive at Earth around midday UTC on June 8th. NOAA's 3-day forecast, published at 12:30 on June 7th, called for the peak planetary K-index of KP7, the G3 threshold, to occur during the 18 Cotiniti window on June 8th. 2 G3 watches, 6 days apart, from 2 different sunspot regions. In the same week, that is the pattern that matters. Not just the individual storm intensities, which are significant but not extraordinary on the historical scale. The pattern of consecutive, overlapping, back-to-back solar events is what elevates the risk profile. Each event in isolation is manageable. The grid can handle 1 G3, the satellites can handle 1 storm. The operators can work 1 set of extended overnight shifts. What becomes genuinely challenging is when the events stack, when the recovery window between storms is compressed, when equipment that was already thermally stressed during the first event faces a second event before it has fully cooled, when the operations teams that managed the first storm are still writing their post-event reports when the second storm warning arrives. At this point in the story, we need to talk about the single most important variable in geomagnetic storm forecasting, the one factor that determines more than any other whether an incoming CME produces a minor inconvenience or a historic catastrophe. The factor that has humbled space weather forecasters repeatedly over the decades, and that represents the central unsolved problem in operational space weather prediction. It is the magnetic field, specifically, the orientation of the magnetic field embedded inside the incoming CME. Here is how it works. Earth is surrounded by an invisible magnetic bubble called the magnetosphere. It is generated by the churning liquid iron in Earth's outer core, Our planet has a natural electromagnetic dynamo at its center, and the magnetic field it produces extends outward into space, forming a protective shield that deflects the solar wind around us. Without this shield, the solar wind would have gradually eroded Earth's atmosphere over billions of years, the way it appears to have done to Mars, which lost most of its global magnetic field early in its history, and now has only a thin remnant of atmosphere. The magnetosphere is remarkably effective at deflecting the solar wind under normal conditions. The solar wind flows around it the way water flows around a streamlined rock. Most charged particles in the solar wind never enter Earth's magnetic environment. They get deflected around it and continue outward into the deeper solar system. But the magnetosphere has a specific vulnerability. It is not equally protective in all circumstances. The degree of protection it provides depends critically on the orientation of the magnetic field carried by the incoming solar wind relative to Earth's own magnetic field. When the two fields are aligned in the same direction, when the incoming field points northward, the same direction as Earth's field on the sunward side, the two fields push against each other, like trying to push two bar magnets together with matching poles facing. The solar wind energy bounces off, the shield holds. But when the incoming field points in the opposite direction, when it is oriented southward, something fundamentally different happens. Instead of repelling each other, the two opposing fields connect. They link up through magnetic reconnection, the same physical process that drives solar flares, now operating at the boundary of Earth's magnetosphere, and in doing so they open actual channels in the magnetic shield through which solar wind plasma can pour directly into Earth's magnetic environment. The energy transfer rate from the solar wind into the magnetosphere spikes. Charged particles funnel down magnetic field lines into the polar regions and collide with atmospheric gases, producing the aurora. The ring current of energetic particles circling Earth in the equatorial plane of the magnetosphere intensifies, compressing Earth's magnetic field and producing the geomagnetic disturbance that manifests as the rapidly fluctuating compass readings, the induced ground currents, the GPS errors, and the satellite charging that we measure and forecast. Scientists call this critical variable BZ, the Z component of the interplanetary magnetic field measured in nanoteslas. When BZ is positive, the incoming field is northward, the magnetosphere holds. When BZ goes negative, the field is southward, the shield begins to fail. When BZ goes strongly negative, when it drops to -20, -30, -50 nanoteslas or below, and stays there for hours at a time, you get the major geomagnetic storms that end up in the history books, the ones with KP8 and KP9, the G4s and G5s, the ones that damage transformers and generate auroras in Florida. The brutal and fundamental problem with space weather forecasting is that we cannot know the Bs of an incoming CME until it arrives at the D-Space spacecraft at the L1 Lagrange point, 1.5 million miles from Earth, with a solar wind transit time from that point to Earth of 15 minutes to 60 minutes depending on the solar wind speed at the time. Everything before that moment, all the careful analysis of coronagraph imagery, all the WSA-Enlil model runs, all the expert judgment of the forecasters at SWPC is working with indirect information, the internal magnetic field structure of a CME, which evolves as it travels and is modified by its interaction with the ambient solar wind, and by any merging events like the Cannibal scenario we've described, is not directly measurable until the material is essentially at our doorstep. This is why a G3 watch sometimes produces a G2 event, as happened with the June 3rd storm. It is why a G2 watch sometimes produces a G4 event, as has happened in the historical record when a CME arrived with an unexpectedly strong southward BZ. The forecast gives you the best estimate of what is probable given what is known. The BZ is what determines what actually happens. There is no more frustrating or more important limitation in all of applied geophysics. Researchers have been working on this problem for decades. Models that try to predict the internal magnetic structure of CMEs from the characteristics of their source flares exist and have shown some skill in research settings. Spacecraft concepts for positioning sensors further sunward, at the L4 or L5 Lagrange points, 60 degrees ahead and behind Earth in its orbit, which would give hours rather than minutes of additional warning, have been proposed and studied by both NASA and the European Space Agency. But none of these solutions are operational yet. DSCO via L1 remains the primary sentinel, giving us the warning window we have, and the space weather community works within that constraint as skillfully as the physics allows to understand why 2 G3 events in 6 days is notable rather than routine. You need the context of where we sit in the 11-year solar cycle. Because the sun's activity is not constant, it rises and falls on a predictable rhythm, and where we are in that rhythm determines the baseline probability of events like the ones we have just been through. solar cycle 25 began at its minimum in December 2019. Before it started, an international panel of the world's top solar scientists, convened by NOAA, NASA, and the International Space Environment Services, made a detailed prediction about how it would unfold. The consensus forecast was for a weak cycle. The panel predicted a maximum smoothed sunspot number of 115, a peak expected around July 2025, and described the upcoming cycle as likely to be similar in strength to solar cycle 24, which had itself been the weakest solar cycle in approximately a century. The prevailing view in late 2019 was, do not worry too much about solar cycle 25, it is going to be quiet. The sun is taking a rest. That prediction was wrong. Thoroughly, completely, embarrassingly wrong, not through any fault of the scientists who made it, but because the sun had other plans. By January 2023, just over 3 years into the cycle, solar cycle 25 was already running 12% hotter than cycle 24 had been at the same point. The sunspot numbers were climbing faster than predicted. The rate of M and X-class flare production was exceeding the models. NOAA revised its forecast completely in October 2023, rewriting the prediction to call for a peak between January and October 2024 with a maximum sunspot number between 137 and 173, nearly 50% higher than the 2019 forecast had predicted. The sun had not gotten the memo about being quiet. It had decided to be active, and it was not asking for anyone's permission. In the summer of 2024, sunspot counts reached a 23-year high. In October 2024, solar cycle 25 produced an X9-point flare, one of the most powerful single flares of the modern satellite era, and in May 2024, active region 3664 delivered the storm that really woke the public up to what solar maximism looks like in the 21st century. AR 3664 appeared in early May 2024 and spent several days producing a cluster of X-class flares and multiple CMEs. The resulting geomagnetic storm was rated G5, extreme, the highest level on NOAA's scale. The planetary K-index reached 9, the DEAST index, the measure of how severely the solar plasma is squeezing Earth's magnetic ring current, plunged to negative 412 nanoteslas, one of the deepest readings since the early 2000s. This was the most powerful geomagnetic storm since the Halloween events of October and November 2003, and the aurora went everywhere. People in Florida saw the northern lights for the first time in their lives. People in Mexico saw them. Images of green and pink aurora shimmering over places that have no business being anywhere near. The auroral zone went viral across every social media platform on the planet. It was genuinely beautiful, but beauty was not the only consequence. The GPS disruptions during the May 2024 G5 storm caused positioning errors that rippled through agriculture, construction, surveying, and precision navigation in ways that took weeks to fully account for. Reports that emerged in the following months estimated a loss of approximately $500 million to the US agricultural industry alone during that brief storm period, driven by precision GPS failures during critical spring planting operations. That number, $500 million from a single space weather event to just one sector of one country, is the kind of concrete, economic framing that helps people understand why space weather preparedness matters beyond the science. After the May 2024 peak, solar cycle 25 did not collapse into sudden quiet. The cycle declined from its G5 peak, but not steeply, and in early 2026 it showed renewed vigor. In late January 2026, active region 4066 emerged and became one of the most prolific individual sunspot groups in the entire cycle, producing 5 X-class solar flares in just 2 days. By the time AR 4366 rotated out of view, it had accumulated 21 C-class flares, 38 M-class flares, and 6 X-class flares from a single region during a single solar rotation. Spaceweather.com described it as shaping up to be the most active sunspot of the cycle to that point, and now 4 months later, AR 4455 has arrived with its anti-hail configuration and its extraordinary 10-hour 3-flare burst, followed immediately by AR 4461 with its filament eruption, with AR 4455, AR 4458, and AR 4459 all still on the Earth-facing disk, and all still carrying the beta-gamma or higher magnetic complexity classifications that indicate ongoing flare potential. The question that every space weather forecaster is sitting with right now is whether solar cycle 25 is simply declining from its 2024 peak in a relatively slow and active way, which is well within the normal range of how solar cycles behave, or whether it is exhibiting the double peak structure that solar physicists call the Neveshev gap phenomenon. The Neveshev gap, first described by the Soviet solar physicist Mikhail Neveshev in the 1960s, is a dip in solar activity that occurs between 2 distinct peaks in many solar cycles. The first peak rises and falls, there is a brief quieter period, and then activity rises again to a secondary maximum before finally declining toward the next minimum. Some cycles show this clearly, others do not, and the only way to tell which kind of cycle you are in is to watch it unfold. If solar cycle 25 is in a double peak structure, then what we are seeing in early June 2026 could be the beginning of the secondary rise. That would mean the coming months, the rest of 2026 and potentially into early 2027 could bring sustained elevated solar activity, more complex active regions rotating into the Earth-facing zone, more M and X-class flares, more CMEs, more geomagnetic storms. Not necessarily more G5 events, but a continued elevated probability of G3 and G4 events above the baseline rate that a declining cycle would predict. This is not a prediction. It is a possibility that the data does not yet allow us to rule out. The space weather community will be watching the monthly sunspot numbers and the active region complexity metrics carefully over the next several months to get a cleaner read on the cycle's trajectory. Let us step back now from the immediate data and spend time with the history of solar storms and humanity's relationship with them. Because that history is one of the most remarkable and underappreciated stories in the history of technology, and the events of this week sit at a specific and meaningful point in that long arc. Before the 19th century, humans had essentially no awareness of solar storms as a distinct phenomenon. The sun rose, it shone, it set. Astronomers observed sunspots. Galileo had noted them in the early 17th century, but the idea that the sun could reach across 93 million miles of space and damage infrastructure on Earth's surface was not part of anyone's thinking, because there was no infrastructure sensitive enough to be damaged. The most sophisticated electromagnetic technology of 1800 was a compass needle, and compass needles do deflect during strong geomagnetic storms, but nobody in 1800 had connected that observation to anything happening on the sun. The telegraph changed everything. When the first commercial telegraph lines appeared in the 1840s and expanded rapidly through the 1850s, humanity had for the first time built a global network of long metal conductors, copper wires strung on wooden poles across thousands of miles of landscape. These wires were, without anyone realizing it, perfect antennas for picking up geomagnetically induced currents. Long conductors in the ground, spanning from city to city and coast to coast, were exactly the kind of infrastructure that a major solar storm could reach. The discovery came suddenly. On September 1st, 1859, the British amateur astronomer Richard Carrington was at his telescope in his private observatory, doing what he did every clear morning, carefully sketching the positions and shapes of sunspot groups visible on the solar surface. He had been doing this for years. He was a patient, meticulous observer who had contributed serious work to solar astronomy, and on that morning he saw something that had never been reported before. A sudden, intense brightening appeared near one of the sunspot groups, two brilliant white points of light, so bright they were visible through his darkened solar filter, flared up and swept rapidly across the surface before fading in under 5 minutes. Carrington stared in disbelief, then ran to find a colleague to witness it. By the time his colleague arrived, the flares had faded. He reported the observation to the scientific community, and noted that approximately 17 hours later, a massive magnetic storm struck Earth. He was careful not to claim a direct connection. The science of the time did not yet establish it, but he noted the coincidence and let the data speak. The magnetic storm that struck Earth on the night of September 2nd, 1859 was unlike anything in recorded history. Telegraph systems across North America and Europe failed in ways that operators had never experienced and could not immediately explain. Telegraph lines that were working perfectly suddenly began transmitting garbled messages with no apparent cause. Others stopped transmitting entirely. Operators who attempted to use their equipment received electric shocks when they touched the keys and terminals. Some telegraph offices reported sparks and fire from the equipment. In Boston and Portland, Maine, operators made a remarkable discovery. When they disconnected their battery power sources entirely, they found that the geomagnetically induced currents flowing through the telegraph wires were powerful enough to operate the system without any external power at all. They spent 2 hours transmitting messages to each other purely on aurora power. The aurora itself was visible across the entire planet and reached intensities that nobody alive had ever seen. In New England and the mid-Atlantic states, people woke up thinking the sun had risen early because the aurora was so bright. Gold miners in the Rocky Mountains got out of their bedrolls and started making breakfast, convinced that dawn had arrived. It was the middle of the night, and the aurora was providing daylight-equivalent illumination. In Cuba and the Bahamas, where the northern lights had never been observed in living memory, people panicked. In Australia and New Zealand, the southern aurora appeared overhead in equatorial latitudes where it had never been recorded, visible through the entire night. Modern estimates of the Carrington event's intensity, reconstructed from historical magnetometer records and from nitrate deposits in ice cores that preserve a chemical signature of the particle radiation associated with the accompanying solar proton event, put the minimum dist somewhere below -800 nanoteslas, perhaps as low as -900 or beyond. For comparison, the May 2024 G5 event reached -412 nanoteslas. The Halloween storms of 2003 reached around -383. The Carrington event, by these estimates, was approximately twice as intense as the most extreme storm of the modern satellite era. It was a different category of event entirely. For the next 44 years after Carrington, the world continued building its electrical infrastructure without fully reckoning with the solar storm risk. The telegraph network expanded. The first transatlantic cables were laid. Edison's electrical distribution systems appeared in the 1880s. Long-distance electrical transmission lines began connecting power plants to cities in the 1890s. All of this infrastructure was sensitive to geomagnetically induced currents, and significant solar storms continued to occur through this period. Events in 1882, 1903, and 1909 produced notable telegraph disruptions, but none approached the Carrington level, so the vulnerability never rose to the top of the engineering agenda. The first clear demonstration of what solar storms could do to modern power infrastructure came in March 1989. On March 13th of that year, a severe geomagnetic storm struck Earth, rated at approximately G5 on the modern scale, with a dist around -589 nanoteslas. The Quebec power grid, operated by Hydro-Quebec, collapsed within 92 seconds of the storm's peak. The sequence of events unfolded with terrifying speed. Geomagnetically induced currents flowing through the ground began saturating the iron cores of large power transformers at substations across the system. Saturated transformers began generating harmonic distortion in the alternating current waveform. Protective relays, designed to detect abnormal current patterns and disconnect damaged equipment, began tripping. As more equipment disconnected, the remaining equipment was pushed even harder, causing more harmonics, tripping more relays, until the entire system collapsed into blackout. 6 million people in Quebec and parts of the northeastern United States lost power. The outage lasted up to 9 hours in some areas. Power transformers were damaged. The economic cost was in the hundreds of millions of dollars, and the world's electrical utilities finally had an example, vivid and undeniable, of what a major solar storm could actually do to modern power infrastructure. The lesson from 1989 was eventually absorbed. Hydro-Quebec installed capacitor banks on its transmission lines to block the DC-like induced currents. Other utilities in North America and Europe began developing their own GIC monitoring and protection protocols. The space weather community began working more closely with the utility industry. Progress was made. Then came the Halloween storms of 2003. In late October 2003, active region 10486, one of the largest and most complex sunspot groups of solar cycle 23, produced a series of extraordinary flares. On October 28th, an X17 flare. On October 29th, an X10, and on November 4th, the event that saturated the GOES X-ray detectors, the flare that pegged the instruments at their maximum reading before the event had finished, making it impossible to directly measure the true peak intensity. Post-event analysis estimated it at X28, possibly X34, making it by far the most powerful solar flare ever recorded on modern instruments. The geomagnetic storms that followed reached G5. Sweden experienced widespread power outages. South Africa lost a large power transformer serving millions of customers, a transformer that took 14 months to replace because nothing comparable was available off the shelf. Spacecraft experienced anomalies, orientations were lost, instruments were damaged. The International Space Station crew temporarily sheltered in a shielded module to reduce their radiation exposure. Airlines diverted dozens of polar flights. The economic impact globally ran into the billions of dollars. The Halloween storms were the defining space weather event of the modern satellite era until May 2024 temporarily took that title. They drove a decade of intensified grid hardening, satellite protection engineering, and space weather forecasting improvement. NERC, the North American Electric Reliability Corporation, issued reliability standards specifically addressing geomagnetic storm risks as a direct consequence of the 2003 events. The utility industry invested significantly in GIC monitoring equipment. The FAA improved its space weather advisory protocols for aviation. The Department of Homeland Security included solar storms in its national risk framework. Progress was real, sustained, and meaningful, And then, in May 2024, the G5 that exceeded Halloween in terms of DS depth reminded everyone that progress, however real, is never finished. Here is where we need to have the most honest and careful part of this conversation, because the historical record and the physics raise a question that deserves a direct and straightforward answer. What would a Carrington-class event do to modern infrastructure? This is not a hypothetical that responsible scientists wave away. It is a question that has been addressed in formal technical reports by NOAA, NASA, the Federal Emergency Management Agency, the Department of Homeland Security, the National Academy of Sciences, and the U.S. Science and Technology Facilities Council, among others. In January 2026, STFC published the fourth edition of their comprehensive report on worst-case space weather environments, specifically to give governments and infrastructure operators a grounded, quantified answer to this question. The probability of a Carrington-class event in any given year is low. Estimates range from roughly 0.5% to 2% per year, depending on the methodology. In any given decade, the probability of experiencing a Carrington-level event is somewhere in the range of 5% to 12%. Low, but not negligible, and when the consequences of the event are severe enough, even low probability risks warrant serious investment in prevention and mitigation. The power grid is the most critical vulnerability. The United States electrical system serves 330 million people through a network of generation plants, transmission lines running at up to 765,000 volts, and a hierarchy of transformers that step voltage up and down between generation and end use. The critical bottleneck from a geomagnetic storm perspective is the large power transformers at high-voltage substations, the enormous house-sized machines that handle the voltage transformation at the 345 kV and 500 kV transmission levels. These transformers are custom manufactured to order. They weigh hundreds of tons. They cost $5 to $20 million each, depending on size and specifications. They require 12 to 18 months to manufacture, and they are not stockpiled. When one fails, the utility orders a replacement and waits. A 2008 report from the National Academy of Sciences, titled Severe Space Weather Events: Understanding Societal and Economic Impacts, estimated that a Carrington-class storm could damage 300 or more large transformers in the United States alone. With a 12 to 18-month replacement timeline and no stockpile, the consequence of losing 300 transformers simultaneously would be widespread, prolonged power outages across large regions of the country. The 2008 report estimated economic damage of $1 to $2 trillion with a recovery timeline of 4 to 10 years in the worst affected areas. Subsequent analyses have revised some of these figures, both upward in some scenarios and downward in others, depending on assumptions about grid protective measures and the exact storm geometry. But no credible analyst has argued that the order of magnitude is wrong. GPS failure would be the second major immediate consequence. As discussed in detail earlier, GPS is woven into modern infrastructure at a depth that goes far beyond navigation. The precise timing signals broadcast by the GPS satellite constellation are used by cellular networks to synchronize base stations, by financial exchanges to timestamp transactions, by power grid management software to coordinate operations across thousands of miles, by internet backbone routers to maintain synchronization, and by air traffic control systems as a primary timing reference. Loss of GPS, which a Carrington-level ionospheric disturbance could produce for days to weeks, would cascade through all of these systems in ways that are difficult to fully predict because the dependencies are complex and often undocumented. Some systems have backup timing sources, ground-based reference clocks, alternative synchronization protocols, battery-backed timing modules that can bridge short gaps. But many do not, and the systems that lack backups are not always the ones you would expect. The vulnerability is distributed, hidden in the assumptions baked into infrastructure that was designed when GPS was assumed to be continuously available. Satellite damage would be the third category of catastrophic impact. A Carrington-class event would subject every satellite in low Earth orbit to radiation environments and atmospheric drag conditions far exceeding what most satellites were designed to survive. The current low Earth orbit satellite population includes several thousand operational spacecraft, including the GPS constellation itself, the Starlink and OneWeb broadband constellations, the International Space Station, hundreds of weather and Earth observation satellites, military reconnaissance and communication spacecraft, and thousands of smaller commercial and scientific satellites. A Carrington-level storm would damage electronics through radiation, destroy vulnerable solar panels through particle bombardment, accelerate orbital decay through extreme atmospheric drag, and potentially cause catastrophic failures across a significant fraction of this population. Replacing even a portion of this orbital infrastructure would take years and cost hundreds of billions of dollars. Now, and this point requires equal emphasis to everything above. None of this is the situation we are in during a G3 event like the ones we are discussing this week. The gap between G3 and a Carrington event is vast. G3 is manageable. G3 is what operational space weather preparedness was built to handle. The reason to describe the Carrington scenario in the context of a G3 week is not to imply that G3 escalates to Carrington. It is to give you the full range of what this phenomenon is capable of. The complete picture that allows you to understand why governments and utilities and satellite operators and aviation authorities treat space weather seriously enough to have dedicated monitoring systems, dedicated operational protocols, and dedicated teams of professionals whose entire job is to watch the sun and protect the infrastructure when it acts up. At this point, you have the full context. You understand what happened on June 3rd, what a Cannibal CME is, why AR4445 was unusual, what G3 means on the storm scale, what the BZ variable determines, what the history of solar storms tells us, and what the realistic worst-case scenarios look like. Now let us talk about what you should actually do with all of this information. The most important thing is to know where to get real, authoritative, official information on space weather in real time. The answer is NOAA's Space Weather Prediction Center. Their website at swpt.gov is the authoritative source for all official US space weather products, watches, warnings, alerts, real-time KP index readings, solar wind data from DSOVR, and the 3-day forecast. It is free, it is always current, and it is written by the best operational space weather team in the world. If you are serious about tracking this event or any future space weather event, that website is your primary tool. SWPC also offers email and text subscriptions for space weather alerts. You can sign up to receive automatic notifications when watches, warnings, or alerts are issued at specific threshold levels. For people who work in industries with significant space weather exposure, utilities, aviation, satellite operations, precision agriculture, construction, survey work, setting up these notifications is a simple and free way to have an early warning system that requires no ongoing attention on your part. For tonight specifically, here are the practical things worth knowing. If you are in a northern tier state, Montana, Wyoming, Idaho, the Dakotas, Minnesota, Wisconsin, Michigan, upstate New York, Vermont, New Hampshire, or Maine, there is a real and meaningful possibility of aurora borealis visible tonight during the G3 peak window, which the SWPC forecast places in the 18 to 21 UTC range, corresponding to roughly 2 to 5 p.m. Eastern, which means the sky will be dark enough for aurora viewing by approximately 10 p.m. local time in most of that region. You do not need any special equipment. You need clear sky, a location away from city lights, and patience. Drive 20 to 30 miles outside of any significant urban area. Let your eyes adjust for 10 minutes after turning off your car headlights. Look low on the northern horizon first. Aurora during moderate storms often appears as a diffuse greenish glow close to the horizon before developing into higher structure. Use your smartphone camera with night mode enabled. Cameras are far more sensitive to aurora than the naked eye, and will often show colors and structure you cannot detect visually. If you are flying tonight, particularly on a long-haul international route that crosses high latitudes, your airline's operations team has already received all relevant NOAA advisories and has protocols in place. The most likely operational consequence is a minor routing adjustment and possible extended reliance on satellite communication rather than HF radio. None of this creates any danger to the flight. Airlines have been operating through space weather events for decades. If your power goes out tonight and you are in a northern tier state, space weather is a possible contributing factor, but so are dozens of other more mundane causes. A downed tree, a failed transformer that had nothing to do with the sun, a car hitting a utility pole. Do not assume space weather connection without checking. If the KP index on the SWPC website is at 7 or above and your utility reports widespread outages across a large region with no other obvious cause, that is when the space weather explanation rises above the noise. If you use precision GPS for professional purposes, survey work, precision agriculture, construction staking, aerial survey, precision approach navigation, plan your most accuracy-critical work for the periods outside the peak storm window and the 12 to 24 hours following it, when the ionosphere is recovering. The worst GPS accuracy during a geomagnetic storm comes during the active disturbance and during the ionospheric recovery phase that follows. For everyone, the most important practical preparation for space weather events is exactly the same as the most important practical preparation for any significant natural hazard. Know where your important documents are. Have a plan for communication if your phone network is degraded. Have a few days of water and food in your home if you live in a region where an extended power outage is a realistic concern. Charge your portable power banks. Know the location of your nearest emergency shelter. These are not dramatic or exotic preparations. They are the same common-sense resilience measures that FEMA recommends for hurricanes, ice storms, and any other event that can interrupt power and services for an extended period. Space weather is one of the few natural hazards that can, in an extreme scenario, produce extended, widespread infrastructure disruption simultaneously across an entire hemisphere. Most natural disasters are geographically limited. A hurricane hits a region, a tornado hits a town, a flood affects a watershed. A major solar storm affects everywhere on Earth simultaneously. That geographic reach is what makes the most extreme scenarios particularly challenging from an emergency management perspective, because the mutual aid networks that allow regions to help each other after a disaster are premised on the assumption that the next region over has resources to share. In a severe geomagnetic storm, the next region over may be facing the same situation. As of the morning of June 8, 2026, the CME from the June 6 AR4461 event is en route to Earth with an expected arrival around midday UTC. The SWPC 3-day forecast calls for the peak G3 window during the 18 to 21 period, followed by a gradual decline through G2 conditions on June 9th and a return toward quiet conditions by mid-UTC day on June 9th, assuming no additional CME activity. That last phrase, assuming no additional CME activity, is the qualifier that matters. As of the latest solar region summary, AR4455 and AR459 are still on the Earth-facing solar disk and still carrying beta-gamma or higher magnetic complexity classifications. Beta-gamma is the classification that indicates a sunspot region has the kind of mixed-stressed complex magnetic field structure that is capable of producing M-class and potentially X-class flares. 3 beta-gamma regions simultaneously on the Earth-facing disk is, as EarthSky noted in their May 29th solar activity report when AR4455 first revealed its complexity, a noteworthy situation. The more complex regions on the disk at any given time, the higher the baseline probability of additional significant flares. Separately, AR4461, whose filament eruption launched the June 8 CME, appears from recent imagery to have lost its more complex magnetic configuration as of June 7th, which reduces the immediate risk of additional major activity from that specific region. But the other active regions are still very much present and active, and the Sun's rotation is continuously bringing new regions around from the far side. The next 2 weeks will see the current set of active regions rotate off the western limb and a new set, whatever is currently on the far side, rotate into view from the east. The character of that incoming population is unknown until the regions become visible. What the space weather community will be watching most closely in the days immediately following the June 8th storm is the solar wind recovery. After a major CME passes, the solar wind gradually returns to background conditions, lower speed, lower density, weaker magnetic field, over a period of hours to days. The rate of that recovery determines how quickly the ionosphere and the magnetosphere return to their normal quiet configurations, and therefore how quickly GPS accuracy, satellite operations, and radio communications normalize. If another CME arrives before that recovery is complete, if the active regions still on the disk produce another significant eruption in the next 24 to 72 hours, while the magnetosphere is still disturbed from the June 8th event, the compound effect can produce more significant disturbances than either individual event would have generated. This is sometimes called a preconditioning effect. The first storm opens the magnetosphere, the second exploits the opening, and the result is a more severe combined event than the individual storm intensities would predict. This is one of the less commonly discussed but operationally important aspects of solar storm sequences. Grid operators and satellite managers do not just watch individual storm events in isolation. They track the sequence and timing of events, because the recovery window between events matters enormously for how exposed their systems are when the next event arrives. Let us close with something that goes beyond the data and the forecasts and the operational protocols. Something that I think is worth sitting with, because it is the thought that always comes to me at the end of a week like this one. We have spent the last 150 years building a technological civilization of extraordinary sophistication. A civilization that can sequence the human genome in hours, that can talk to spacecraft beyond the edge of the solar system, that can model the climate decades into the future and place the resulting uncertainty bounds with scientific rigor, that can land a spacecraft on Mars with precision, that can, from a room in Colorado, track a cloud of magnetized plasma traveling at 1 million miles an hour across 93 million miles of interplanetary space, and predict its arrival time to within 6 hours. All of this is real, all of it is remarkable, and all of it sits on a foundation of three things that the sun can reach out and affect: electricity, GPS timing signals, and radio communication. Remove those three things or seriously degrade them, even temporarily, and the extraordinary technological civilization we have built begins to struggle in ways that most people have never had to think about, because in living memory those things have always worked. We built this civilization during a period that, in the long context of solar history, was characterized by relatively moderate space weather. The 20th century, the century during which essentially all of the infrastructure we depend on was designed, built, and interconnected, did not include a Carrington-class event. It included some significant storms: the 1940 storm, the 1958 storm, the 1972 storm that disrupted navigation systems and triggered unintended detonations of naval mines in the Tonkin Gulf, the 1989 Quebec blackout, the Halloween storms of 2003. All of these were serious. None of them were Carrington. We got lucky, and we built our systems, by and large, without fully accounting for the possibility that the star overhead might occasionally do something dramatically outside the range of what we had experienced while the building was happening. The power grid was not designed with Carrington resilience in mind. The GPS constellation was not hardened for a Carrington-class radiation environment. The internet backbone timing infrastructure was not built with the assumption that GPS could be unavailable for 2 weeks. The assumptions embedded in our infrastructure about the reliability of electricity, connectivity, and navigation are assumptions that most engineers made implicitly, without explicitly thinking about the solar storm risk, because the solar storm risk seemed remote, and the budget for addressing remote risks is always limited. The gap between current preparedness and adequate preparedness for the most extreme solar events is real and is documented. Hardening the US power grid to the level that would make it resilient against a Carrington-class GIC event would cost somewhere between $20 and $100 billion, depending on the specific standards adopted and the depth of protection required, against a $1 to $2 trillion damage estimate for a Carrington event striking an unhardened grid. That is an extraordinarily favourable cost-benefit ratio by any analysis. The engineering is understood. The solutions exist. The technology is available. The gap is political will and sustained attention. The unglamorous, undramatic work of infrastructure investment in the face of a low probability, high consequence risk that does not make the news often enough to maintain the political pressure required to fund the work. Events like this week help, not by frightening people, but by demonstrating concretely and visibly that the phenomenon is real. 2G3 watches in 6 days, radio blackouts across Asia and the Pacific, grid operators across the northern United States working extra shifts, satellite operators burning fuel to compensate for increased atmospheric drag. These are not theoretical future risks. They are operational realities happening right now, being managed by teams of people whose existence and whose work most of the public has never heard of. The best outcome of a week like this one, the real value of paying attention to events like the June 3rd AR4455 flare sequence and the June 8th AR4461 CME arrival, is not that it generates dramatic content or viral aurora photographs, though both of those things will happen. The best outcome is that it builds incrementally the baseline of public understanding that makes seriously discussion possible, that more people know what a geomagnetic storm is and what it can do than knew before this week. That more people understand the difference between a G1 and a G5, between a disruption and a catastrophe, between what is happening now and what could happen in a more extreme scenario. That more people can engage meaningfully when the conversation about grid hardening investment comes up in a utility commission hearing or a congressional budget debate or a school board meeting, where someone is wondering why the emergency management department wants to include space weather in the hazard curriculum. The sun is going to keep doing what it does. It will continue through the descending phase of solar cycle 25 at whatever pace and with whatever surprises it decides to offer. Solar cycle 26 will begin sometime around 2030 and will ramp up through the 2030s toward its own maximum. The probability of a Carrington-class event remains what it is, low in any given year but meaningful over decades. The only variable within human control is how prepared we are when it comes. As of the morning of June 8, 2026, the CME launched by Active Region 4461 on June 6 is arriving at Earth. The DESO VR spacecraft at L1 is measuring the incoming solar wind. The GOES-19 satellite is monitoring conditions in Earth's immediate space environment. The planetary K-index is climbing. The 18 to 21 UTTC peak window is approaching. The space weather team at NOAA's Boulder facility is at their workstations. They are watching the BZ, waiting for it to declare itself, northward or southward, moderate or strong. Everything the models have predicted up to this moment is about to be tested against the actual measurement. The warning that was issued 48 hours ago is about to become the reality. Somewhere in Montana, a farmer is going over the day's precision GPS planting plan and wondering if he should run the automated equipment tonight or wait until tomorrow. Somewhere in Manitoba, a grid operations centre has 3 extra technicians on shift who are not normally there on a Sunday night. Somewhere over the North Atlantic, a Boeing crew has just switched from HF radio to satellite communication for their position report because the HF frequencies are too noisy to use. Somewhere in Michigan, a family is driving into the countryside because they saw on the Aurora forecast app that tonight might be the night. All of these people are, in different ways, responding to the same event, to the same cloud of magnetized plasma that left the sun 48 hours ago from a filament eruption on a sunspot group that most of them have never heard of. They are all downstream of the same physics, the same solar atmosphere, the same magnetic reconnection event that flung 1 billion tons of charged particles into interplanetary space on a Friday afternoon. That is the thing about space weather that makes it unlike almost every other natural hazard. It is invisible until it arrives. It travels through space silently, without warning to anyone on the ground until the dedicated instruments catch it. And then, in the span of a few hours, it can touch everything simultaneously. The power lines, the satellites, the radio frequencies, the GPS signals, the magnetic compasses, the aurora, the atmosphere itself. It touches all of it at once because it is not a local event, it is a planetary event, a whole Earth event, driven by a star that will outlive everything we have ever built by billions of years. If you can get somewhere dark tonight and the skies are clear and you are far enough north, go outside, stand in the darkness and look north. Give it 20 minutes. Let your eyes adjust. If the storm performs as forecast, you might see something that most Americans have never seen over their own homes. Green light rippling low on the horizon, or higher if you are lucky. Maybe red above it, maybe a faint violet. The colours depend on which atmospheric atoms the incoming particles are colliding with and at what altitude. Oxygen at high altitudes makes red. Oxygen at lower altitudes makes green. Nitrogen makes blue and purple. Your phone camera will see more than your eyes. And if you see it, know what it actually is. It is not a decoration. It is not an accident. It is evidence of an invisible battle happening above your head between the sun's magnetic field and Earth's magnetic field, a battle that our planet's magnetic shield has been fighting every day for 4.5 billion years. The shield is holding. It is designed to hold. But tonight it is working harder than usual because something very large and very fast just hit it, and some of that energy has found its way through, and it is painting the sky in colours that atoms make when they are excited beyond their normal resting state, and then release that energy as light. It is, in the most literal sense, the sun touching you, reaching across 93 million miles of space and touching the atmosphere above your head. That is what happened this week. That is what is happening right now. Follow NOAA's Space Weather Prediction Centre at swpc.ona.gov for real-time updates. Subscribe to their alerts if you want to be notified automatically when events like this develop. Share this with someone who has never thought about any of it, because the conversation about space weather resilience needs more people in it. The sun is still talking. The question is whether we are listening. Most people have a vague sense that Earth has a magnetic field. They know compasses point north. They may remember from a school science fair project that you can make a compass needle move with a magnet. But the magnetosphere, the full three-dimensional structure of Earth's magnetic environment extending tens of thousands of miles into space, is something most people have never had reason to think about in detail. And understanding it in a little more depth changes how you see the solar storm story entirely. The magnetosphere is not a simple, smooth, symmetric bubble. On the side of Earth facing the sun, the solar wind compresses it. The boundary of the magnetosphere on the day side, the region facing the sun, is pushed inward to roughly 35,000 to 40,000 miles from Earth's centre. On the night side, the opposite effect occurs. The solar wind stretches the magnetosphere out into an enormous elongated tail that extends hundreds of thousands of miles away from Earth, in the direction pointing away from the sun. This tail, called the magnetotail, is where much of the energy from geomagnetic storms is actually stored, and then suddenly released in events called substorms. A substorm is a smaller, faster, more localized burst of geomagnetic activity that occurs within a larger storm. During a major geomagnetic storm like the ones we have been discussing, dozens of substorms can occur over the course of the event. Each one produces a sudden brightening and expansion of the aurora, a sharp jump in the local magnetic field variations measured at ground stations, and a brief but intense surge in the geomagnetically induced currents flowing through power lines and pipelines. From the perspective of grid operators watching their monitoring equipment, a substorm looks like a sudden spike in the GIC readings, often the most damaging single moment in a storm event, because the rate of change of the magnetic field is even more important than the absolute field strength when it comes to driving induced currents. The physics of how substorms are triggered is still an active area of research. The magnetotail accumulates energy, stored in the stretched-stressed magnetic field lines of the tail, over a period of minutes to hours. Then, when some triggering condition is met, the tail snaps back. The magnetic field reconnects explosively in the middle of the tail, releasing the stored energy and sending it both toward Earth as a current surge and outward as a plasmoid, a bubble of plasma that escapes down the tail and into the solar wind. The energy that goes earthward powers the substorm, the auroral brightening, the particle precipitation, the ground currents. This is why geomagnetic storms are not smooth, continuous events. They are episodic, punctuated by the rhythms of substorm loading and unloading. A grid operator watching G levels during a storm does not see a steady, gradually increasing threat that they can manage by steady adjustment. They see sudden spikes, some of which are short enough that automated protection systems handle them, and some of which are sustained long enough to cause thermal damage to equipment that the protection systems were not designed to prevent against. The worst-case moments in a G3 storm are not the average conditions during the event. They are the substorm peaks, which can briefly exceed the average by a factor of 2 or 3. Understanding this episodic character of storm impacts is one reason that operational space weather meteorologists provide not just storm-level forecasts but also substorm activity probability assessments, tools that help grid operators know whether to expect smooth, sustained conditions or sudden sharp spikes during a storm period. This distinction matters enormously for how operators configure their protective settings and how aggressively they reduce load on exposed equipment. When most people think about GPS and solar storms, they think about navigation. Their map app gives them wrong directions. Their car navigation takes them to the wrong address. These are the visible, familiar, relatable consequences of GPS degradation. They are real, and they are also the least important GPS consequences of a significant geomagnetic storm. The more important consequences are the ones buried deep in infrastructure that most people never think about. The consequences that flow not from GPS's navigation function but from its timing function. The GPS satellite constellation, a network of at least 24 operational satellites in medium Earth orbit at altitudes of about 500 miles, broadcasts time signals of extraordinary precision. Each GPS satellite carries multiple atomic clocks accurate to nanoseconds, billionths of a second. The signals broadcast by these satellites are not primarily designed for navigation. Navigation is a derived application. Your receiver triangulates its position by measuring the tiny differences in arrival time of signals from multiple satellites and using those time differences to calculate distance. But the fundamental product of the GPS system is time, incredibly precise, universally available, continuously broadcast time, and the modern world has become deeply dependent on that time signal in ways that have nothing to do with navigation. Cellular networks use GPS timing to synchronize the operations of base stations across a region. Without tight synchronization, base stations interfere with each other and the network degrades or fails. Financial exchanges use GPS timing to timestamp transactions with nanosecond precision. Without that precision, the sequencing of orders becomes ambiguous and market integrity suffers. Power grid management systems use GPS timing to synchronize the measurement of electrical quantities across substations hundreds of miles apart. The phasor measurement units that give grid operators real-time visibility into the state of the transmission system depend on GPS-synchronized measurements to be meaningful. Internet backbone routers use GPS-derived timing to maintain the synchronization that keeps data packets moving efficiently across the network. When GPS signals are degraded during a geomagnetic storm, when the ionospheric disturbances scatter and delay the signals in ways that introduce timing errors, all of these downstream applications feel the effect. Cellular network quality degrades. Transaction sequencing in financial systems introduces uncertainty. Grid state estimation becomes less accurate. Internet routing efficiency decreases. The cascade is subtle but real, and in a sufficiently severe storm it can compound other effects in ways that make the overall infrastructure disruption worse than any single failure pathway would suggest. The dependency on GPS timing has grown steadily over the past 30 years, largely because GPS timing is free, ubiquitous, and extraordinarily accurate. Every system designer who needed a reliable time reference found that GPS provided it with less cost and complexity than any alternative. The result is a world in which GPS timing has been quietly incorporated into thousands of critical systems, often without explicit documentation of the dependency, often without backup timing provisions, and often without the system designers having considered the space weather risks to the GPS signal. Fixing this is not technically difficult. Backup SIM sources exist. Ground-based radio timing systems like ELORAN, dedicated fiber optic timing networks, local atomic clocks maintained at individual facilities, but deploying and maintaining backup timing infrastructure costs money, and the GPS-based solution has been free and reliable for so long that the investment in backup systems has been difficult to justify in annual budgets. The result is a widely recognized but incompletely addressed vulnerability that significant space weather events continue to probe. There is one aspect of solar storm impacts that receives far less attention than the power grid and GPS stories, but that is equally important for specific populations. Radiation. When active region 4455 produced its X1.07 flare on June 3rd, the flare did more than ionize the upper atmosphere and trigger radio blackouts. It also accelerated charged particles, primarily protons, to extremely high energies. These energetic protons travel faster than the CME cloud and can arrive at Earth within minutes to hours of a major flare, depending on the flare's location on the solar disk and the configuration of the interplanetary magnetic field between the Sun and Earth. At ground level, Earth's atmosphere provides enough shielding that energetic solar protons are not a direct health concern for people on the surface. The atmosphere, equivalent to roughly 10 meters of water, absorbs them before they reach us. But at aircraft cruise altitudes, typically 35,000 to 40,000 feet, or about 10 to 12 kilometers, the atmospheric shielding is much thinner. Passengers and crew on commercial aircraft receive an elevated radiation dose during solar proton events, particularly on polar routes where the geometry of the magnetic field funnels more particles into the upper atmosphere. The doses during typical moderate solar events are small compared to occupational health thresholds. But for frequent flyers, for pregnant flight attendants, and for anyone making a long-haul polar flight during a major solar proton event, the additional dose is worth tracking. The FAA tracks space weather radiation exposure for aviation and works with NOAA SWPC to issue advisories when solar proton events exceed levels that require attention. Airlines operating polar routes use these advisories to make decisions about routing, dropping to lower altitudes where the shielding is better, or routing around the polar regions entirely to avoid the highest dose corridors. These decisions add flight time and fuel cost, but they are a standard part of polar route operations during active space weather. For astronauts on the International Space Station, the radiation situation is more serious. The ISS operates at roughly 250 miles altitude, above most of Earth's protective atmosphere, and the crew receives continuous elevated radiation exposure compared to people on the ground. During a major solar proton event, the dosing rate for ISS crew members can spike to levels that require them to shelter in the most shielded part of the station, typically the Russian segment, which has denser material surrounding it. NASA monitors solar proton flux in real time and has protocols for crew notification and sheltering that activate when proton levels reach specific threshold. The June 3rd flares from AR4455 were associated with some particle enhancement, though the position of the region on the solar disk, in the northwestern quadrant, was not the optimal geometry for producing a major solar proton event at Earth. The best connected geometry for Earth-impacting proton events is when the source region is in the western portion of the solar disk. AR4455's position produced some particle flux, but not at the level that would have triggered formal radiation storm alerts. The June 6th AR4461 event similarly did not produce a significant proton enhancement at Earth. This is worth noting as part of the honest accounting of this week's events. The radiation component, sometimes the most immediately dangerous aspect of a major solar event for astronauts and high-altitude aviators, was limited this week because the geometry was not favorable. A different flare location, producing the same energy release but from the southwestern quadrant of the solar disk, could have accompanied the CME events with a significant solar proton event that would have added substantially to the operational challenges of the week. Behind every NOAA alert, every storm watch, every satellite operator notification, and every grid manager advisory is a community of people whose work most Americans have never thought about but whose contributions to civilizational safety are as consequential as the work of weather forecasters, air traffic controllers, and public health officials. The space weather operational community in the United States is centered at NOAA's Space Weather Prediction Center in Boulder, Colorado. SWPC maintains a 24-hour-a-day, 365-day-a-year operational watch for space weather events. On any given day, including weekends, holidays, and the middle of the night, there are trained space weather forecasters at workstations in Boulder watching the sun, watching the solar wind, watching the magnetosphere, and watching the real-time grid and satellite data feeds that tell them what the current event is actually doing to the infrastructure they are responsible for protecting. These forecasters hold specialized expertise that combines solar physics, magnetospheric science, ionospheric physics, and operational meteorology into a discipline that does not have a clean undergraduate curriculum. People who end up doing this work tend to have come from physics, astronomy, electrical engineering, or atmospheric science programs, and then trained specifically in space weather applications on the job, or through NOAA's own training programs. There are not many of them. The entire operational space weather forecasting workforce in the United States numbers in the dozens to low hundreds of people, depending on how broadly you define the community. They work in close coordination with partners across the government and internationally. The UK Met Office runs a joint space weather operations centre with NOAA staff, providing continuous forecasting coverage that is geographically and institutionally distributed for resilience. The European Space Agency's Space Weather Coordination Centre in Brussels coordinates European member states' space weather services. Japan Aerospace Exploration Agency operates space weather monitoring for the Asia-Pacific region. Australia's Bureau of Meteorology maintains a space weather service for the Southern Hemisphere. The International Space Environment Services coordinates data sharing and joint forecasting products among all of these national and regional services. The research community that supports operational space weather forecasting is larger and more distributed, spread across NASA centers, university departments, national laboratories, and international research institutes. The scientists at NASA's Goddard Space Flight Center who analyze SOHO and SDO imagery, the heliophysics researchers at the University of Colorado, Stanford, Rice University, and dozens of other institutions who study CME propagation, magnetospheric dynamics, ionospheric physics, and solar cycle prediction. The engineers who design and operate the spacecraft that collect the observations that make forecasting possible. This community produced, in real time during the week of June 3rd through 8th, 2026, a sequence of watches, warnings, alerts, and advisories that gave the operational users of their products, grid operators, satellite managers, aviation authorities, pipeline companies, military organizations, the advance notice they needed to take protective action. The watches for G3 conditions went out hours before the storm arrived. The real-time updates tracked the actual storm evolution and revised the forecast as new data arrived. The post-event analyses will document what happened, evaluate how well the models performed, and identify where forecast improvements are needed. This is how operational space weather protection works. It is not dramatic. It does not look like the heroic crisis response scenes that movies portray. It looks like people sitting at computers, watching numbers on screens, writing bulletins, updating websites, making phone calls to utility partners, and doing the patient, continuous, unglamorous work of keeping the information flowing so that the people and organizations that need it can do their jobs. They are very good at it. And most of the people who benefited from their work this week, the grid operators who made protective adjustments, the satellite operators who managed their constellations through the storm, the airlines that adjusted their routing, the agricultural GPS users who postponed precision work, did so without knowing anything specific about the M93 flare at 1:36 on June 3rd, or the anti-hail magnetic configuration of AR4455, or the Cannibal CME dynamics that made this week's events particularly interesting from a scientific perspective. That is the system working correctly. The warning reaches the people who need it, they take appropriate action, the infrastructure holds, and the public continues its day unaware that something significant just happened in the relationship between Earth and the Sun. June 8, 2026. The second G3 watch of the week is open. The CME from AR4461 is here. Somewhere over Montana, someone is seeing the northern lights for the first time in their life and taking a photograph with their phone that they will remember forever. Somewhere in Colorado, a space weather forecaster is watching the BZ tick negative on their DSCO-Z display and updating the storm level estimate. Somewhere in a utility control room in the upper Midwest, a grid operator is watching a transformer's temperature readout and deciding whether to reduce load on that circuit before the peak of the storm. Somewhere over the Atlantic, a flight crew has switched to satellite communication for their position reports because the shortwave frequencies are too noisy to use. All of them are connected by the same event, by the same cloud of magnetized plasma that AR-4461 threw into space 2 days ago. By the same sun that threw it, the sun is not done. It will not be done for a very long time. It will continue producing active regions, continuing to fire flares, continuing to launch CMEs into the interplanetary medium for the remaining roughly 5 billion years of its main sequence life. Solar Cycle 25 will complete its decline over the next several years. Solar Cycle 26 will begin around 2030 and ramp up through the 2030s toward its own maximum. Another cycle will follow, and another. The rhythm will continue. Against that backdrop, the events of this week are small: a G3, a Cannibal CME, a fascinating anti-hail sunspot, small measured against the sun's history and its future and its capacity, but not small measured against us. Measured against the civilization we have built, the infrastructure we depend on, the fragile, extraordinary technical achievement of modernity that sits in the path of whatever the sun decides to send our way. Measured against us, a G3 is significant, a G5 is serious, and a Carrington event is a planning scenario that our civilization has not yet fully prepared for. The gap between what we have built and what the sun can do remains. The work of closing that gap, the grid hardening, the satellite resilience investment, the GPS backup infrastructure, the space weather forecasting improvement, the policy and regulatory frameworks that make utility resilience investment economically viable, continues. It continues in technical committees and regulatory proceedings, and budget negotiations and research laboratories and spacecraft design reviews that most people will never hear about. And then, occasionally, the sun does something visible. Something that cuts through the routine and reminds people that the star at the center of our solar system is an active, dynamic, powerful entity that our civilization exists in relation to, not separate from, not protected from by default, but in active, ongoing, consequential relationship with. This week was one of those moments. 2 flares in 10 hours from an unusual anti-hail sunspot, a Cannibal CME tracked across 90 million miles, 2 G3 watches in 6 days, a G2 storm that reached grid operators and satellite managers and aviation teams across the northern hemisphere, and now the second storm, arriving on schedule, doing exactly what the models said it would do, managed by exactly the people and systems that were built to manage it. The sun talked. We listened, the infrastructure held. Keep watching the sky.